Now we go on to chapter 14, which has a lot of content in it, but the title's partial derivatives. That's just a piece of what we do, of course. So this is like doing Calc 1 single variable all over again, but now we're going to be using multiple variables and defining those concepts. So it should look familiar of kind of the progression through the chapter, but we're doing it now with 3 dimensions and several variables. So 14.1 is functions as several variables, defining that, talking about domain, talking about range, talking about something called level curves or level surfaces, and just kind of getting familiar with the concept of a function of several variables, which we actually have already seen. So for single variable, we often write functions of like f of x, g of x, h of t, those sort of things. So what we're going to define is a function of, for right now, 2 variables, f of x, y, equal to z, and what that might look like. And we've already actually seen some of this. Like if I wrote z equal to x squared plus y squared, what is that? Or if I wrote z equal to x squared minus y squared, what is that? And we know the first one is this is a paraboloid, right? So it's a paraboloid that opens up like that, centered at 0. And the other one is the saddle, which I never can draw, right? So it's the saddle x squared minus y squared. And those are what we would say are functions of x and y. When you look at other cases, they're not functions. So let's go ahead and define it and then move forward. So here's the definition. A function of 2 variables is a relation, so it's like a correspondence, etc. So it's a relation such that for each ordered pair x, y in D, in a domain, so it's basically, it'll be a region in the xy plane, or the entire xy plane, essentially. There exists a unique number f of xy and then that's in R, that's in reals, in the real, like a real number line. D is called the domain, so D is called, just like before, the domain. So what I want, you got to start thinking of this stuff as a map. It's a mapping from one set to another. So D is a region in the xy plane. So if I write just our typical xy plane here, this is x and this is y, then I'm going to have D is some region here. Okay, so that's D. And I'm going to map into the real axis. So over here is like a real number line. That's your f of x, y. So this is basically your z equal to f of x, y. So if I have a, say like an ordered pair over here, say A, B, then that maps, so maybe right here, that maps to a point over here on this number line, and this is your f of A, B. So it's a mapping, here's your f from one set to a real number line. And it's unique, so it's like a function. So you don't get this case where you would have, so you don't get this, where you get the same value mapping to another point. okay, then that's not a function, right? So same idea as before. Another way to look at this is how we look at it for a paraboloid and stuff, is you have, let me change that back to not dotted. You have the XY coordinate system, XYZ coordinate system might look something like this. So here's just like our typical XYZ. And you might have, here's your region D in the XY plane. And then that region's down here. Just like that. And then it's going to map to some value on the Z-axis. So this, oops, I knew that was going to happen eventually. Okay, so that's D. And you might have a point here. Here's your XY. And then that maps up to a value up on the Z-axis. Like that. So there's your F of XY. Okay, so a couple examples we've already seen. So let's just write them down here. So if I have A, we could have something like F of XY equal to x squared plus y squared. Okay, and then we know that that's a paraboloid like this, opening up on the like upward, centered at 0. Okay, so you got something like that going. You know, there's so what's your domain, you think, for something like that? So for x squared, y squared, what would domain be? Well, like what could you put in? You can put in anything, right? So you put in any value from 0 and then either direction approaching infinity, anywhere, you're always going to get a value up there on the axis. So nothing. So the domain concept's just like before. We could do the hyperbolic paraboloid. You could do the one that's upside down. I'll just show you another one real quick. We don't want to get used to graphing these anyway. G of xy, 9 minus x squared minus y squared. Right, so that's a paraboloid that opens down like that. Oops, missed that one. We'll go back and erase that. Okay, so that's this paraboloid opening down. That would be like the xy plane, and you can do the same thing. Let's do a real quick sketch. No need to make it too cumbersome here. So that's z equals, you have some value down here. So that's like your AB. And you're going to go up to the graph, and then there's your f of AB, like that. This one, still you can put in any value, 0, and then as you keep on going out on the x-axis and y-axis, it's just going to go farther down and down. You're going to keep going. This thing just keeps on going like that below the axis. So what about a hyperbolic paraboloid? No, I'm sorry. What about a hyperboloid of 1 or 2 sheets, right? So if you have like a hyperboloid like this, is this a function? Okay, and of course the answer is no. You put in a vertical line like that, just like in Calc 1, and it crosses it in more than one place. So not a function. This hits at 2 spots. Oops. Basically here and here, wherever that's going to be. Okay, so that's not a function. But of course, what could we do to make it a function? we can restrict the domain. So we could just say it's up here and then above. And this would be a function, just as long as you don't keep the bottom piece. So yeah, that's true for, a sphere. You just have a hemisphere. That's a function. So we'll be restricting domains just like in calc, any that sort of algebra stuff. Okay, so let's talk about finding domains and sketching domains. So now it's not just on the real numbers, it's the whole xy plane you consider. So let's look at this example. So find the domain and sketch the domain. So we're given f of xy equal to the square root of y minus x. Went way too far on that again. And times the natural log of y plus x. So how do you interpret that? Well, it's it's just like the vector valued functions where you look at the intersection of each of the functions. Now this has basically two functions that are a product. So we have two things going on here. We have that y minus x must be what? That must be greater than or equal to 0. And we have y plus x must be strictly greater than 0. Okay, so if you solve those, you get y is greater than or equal to x. And we have y is strictly greater than negative x. So what's the basic shape of both of those functions? It's y equals x and y equals negative x. So let's graph those. Okay, so it's you're shading basically in the xy coordinate system. That's your domain for two variables. That is. So you're essentially graphing y equals x, and let's change colors because we can, and y equals negative x. So since I have that all ready to go here, the negative x one is going to be this one. So this is your actually. All right, so that's supposed to be dotted, since I might as well do it right away because I can. So that needs to be dotted. Did everyone see why? Because it's a strict inequality here. So it's a dotted line from here all the way to here. And it needs to line up right. Yeah, that's right. All right, so that's one case. And that's my y equals negative x. So I have, though, that y is strictly greater than negative x. So is that going to go up or down? And you can always do it. You can always choose a test value. So that's kind of your fail-safe, is choose a test point. And you can't be on the line, but if you choose like 1, 1, like that, is 1 greater than negative 1? And the answer is, of course, true. So you're going to shade that direction. So everything is this direction. All right, so now let's do the other one. This is y equals x. Like that. And it's solid because it's an or equal to. And this one you shade above, greater than x, so it's going this way as well. I'm not going to do every little thing on this one. It actually goes through 1, 1 on that case. You can't pick 1, 1 again. You got to pick something off of it. So you could pick anything over to the left. You could pick, a value that's like that, and then test, and you'll get a true statement. So one way to this is how we used to do it in when you shaded. So I'm going to use this one. So this basically is shading all this direction like this. So it's all of this. And then the other one, the blue one, is shading all above. So what's the overlapping part? I'm doing this just because I can. It's kind of obvious what it is, right? And then the other one is shading everything this direction. And then what's the overlapping part? You can see that that's the overlapping part. Okay, so that upper corner there is overlapping, and of course that's the domain. So you could describe it. It's everything above the line y equals x, y equals negative x, not including one, not including the other. What about the origin? Is the origin included or not? Right there. Is that included? No, it can't be included because it's dotted. Okay, so we need to make that a circle because you can't. So natural log of 0 is undefined, right? So you can't have natural log of 0. So we're going to erase that. Oops, wrong button. I'm going to erase that with that button. Probably should work fine. So that should be a circle. Okay, looks good. So that's the domain. Okay, so then, and then how would you write that in a set notation? It's really just putting in those two statements. So this is D, that's your domain D. So D is equal to the set xy in R2 such that, and then you just put in those two statements. Y is greater than or equal to x, and y is strictly greater than negative x. So that's really all you can do, and then unless you're asked to go ahead and graph it. Okay, let's try another one. Let's see. So next case, what about this one? So find the domain again. And sketch. So f of xy equal to ln x squared plus y squared minus 4. So another natural log, just to show, what you need to know about natural logs. And the domain of that, what's inside, must be what? So basically you start with a true statement. What needs to be true is x squared plus y squared minus 4 must be strictly greater than 0. And then what is that? Like when you simplify that, x squared plus y squared greater than 0, not 0, 4, you get, that's a circle, right? But it's greater than that, so, and it's not included. So what that is then, if you were to graph that, is a circle. But it's, what is it on the inside, outside? What would you do? So x, y, and I'll do the same thing I did before. Try to make it, it's dotted because it's a strict inequality. And let's see if this can make a circle again. Not too bad. Just move it into place. Close enough. So it's that circle, and then we could actually say what the radius is. So this is 2, and it's not to scale, right? It's just, well, I guess you could say it's to scale, but I didn't put it on the tick marks there. 2 and 2, and then it's inside or out. Yeah, and that's on the outside, of course. So you're going to shade all this stuff out here. So you could test 0, 0 if you wanted to. So if you test 0, 0, you get a false statement, so it must be the other region. So It's all of this. This is your what you're shading. And I'll make it look all pretty with purple because I can with this computer thingy. Okay. So that's the domain. And you could just write that same thing in the domain. All you're saying is essentially this and then the statement. Well, that's true. I mean, that's the statement. And then it's implied. So we need to be able to write both. I'll go ahead and write it. Okay, so the domain, so your domain's out here, is the set xy such that x squared plus y squared is strictly greater than 4. And that's fine. It's implied that that is R2, so you don't have to say stuff like that. Okay, let's try another one. Next example. So what about g of x, y, z equal to the square root of 1 minus x squared minus y squared minus z squared? What about that? So analyzing that a little bit, first of all, this is 4 dimensions. This is a 4D graph. Don't know how to write a 4D graph. What you can do is set it equal to 0, and then you get basically what it is projected into the XYZ plane. We'll talk about that a little bit in a little later. But the domain is in 3D. So the domain is 3D. So we have 1 minus x squared minus y squared minus z squared. What has to be true about that to have real numbers? That must be greater than or equal to. It can be equal to because the square root of 0 is 0. That's okay. It can be equal to 0. And then when you simplify that, you get x squared plus y squared plus z squared would be, and then so I add it and then flip it. That's strictly less than or equal to 1. So what's that going to be? That's basically a sphere of radius 1 is what that is. So sphere radius 1 looks something like that. Back usually make dotted, so you could go in with an eraser like this and make it dotted. Oops, that's way too big, huh? Try that again. So these are dots. That's not going to look very good. That's all right. And then this dotted. So you can take your time on stuff if you want, and make it more like a sketch and erase when needed. Kind of however you feel. You just need to make it look close. So there's your sphere radius 1. Right, so you can kind of go like that if you wanted to. That's your 1. So is it inside of it or outside of it? Inside, yeah. So inside, we actually call that, has a name for it. That's called the unit sphere or unit ball. Unit sphere is going to be used when we define some things a bit later. So the domain's inside that. You can't go outside that, or you will have a imaginary numbers. Okay, let's see. We'll go ahead and do another video for the next couple things on level curves and a few definitions.